Hello everyone, I am Mohammed Tahir Naseem. I'm a graduate student at Physics Department, Koç University, Istanbul. Today I'm going to talk about simultaneous ground state cooling of mechanical resonators. I'm really thankful to my advisor, Professor Özgür, for providing me the opportunity to work on this interesting topic and also for very helpful and fruitful discussions throughout my graduate studies and especially in this project as well. The outline of my talk is following. Although our proposed scheme of cooling is quite general, in fact it only requires a dispersive coupling between the cooling agent and the target systems. Although in order to give an example on the working principles of our scheme, we pick optomechanical systems, which I will briefly describe in the first part of my talk. After that, I will describe typical laser sideband cooling schemes in these systems, and then I will present our proposal, which based on cooling by heating, and finally I will present the results of our scheme. So a typical optomechanical system consists of a cavity mode which interacts with the mechanical resonator, and this cavity is pumped via some external coherent drive. The Hamiltonian of this system is given here. The first part corresponds to the cavity mode, the second one is for mechanical resonator, the third one is a nonlinear term, which is basically the interaction between cavity and the mechanical resonator, the last part associated with input laser drive. And if the system is driven strong enough, then we can use the linearization, in which basically we expand our operator around some mean values. And if we use this linearization process in the optomechanical Hamiltonian, we end up with this result. The important thing to focus here is that we get two types of interaction here. One, which is underlined by red color, is beam splitter type interaction, which is actually responsible for the cooling process in this system, and the other one is two-mode squeezing operator. Interaction, which is basically if this interaction dominates, then our mechanical resonator heats up. So how the sideband cooling works in optomechanical system, in order to understand, let's focus on the lower part of this slide. Here you can see the density of modes, the green line for the cavity mode, and this one is for the mechanical resonator. Omega L is the frequency of the laser frequency. If we select the laser frequency below the cavity frequency, in this case the photon can only into the cavity mode by destroying a phonon from the mechanical resonator. Consequently, we get cooling, and this, in order to have such kind of a process, we need to select detuning. We need to have red detuning, and which leads to beam splitter interaction in the system. On the other hand, if our laser frequency is above the cavity frequency, in this case photon can only enter into the cavity by creating a quanta of energy in the mechanical resonator, and this process can dominate when we have blue detuning in the system. And in this case we get two-mode squeezing interaction, which results in the heating of the mechanical resonator. Here in this slide we have energy structure for the optomechanical system. These are the eigenenergies for the system, where NH shows the number of photons in the cavity, and MC shows the number of phonon in the mechanical resonator. So let's say we start from n photons and m plus 1 phonon in the mechanical resonator, and if our detuning is red detuned, then what happens is we create a high energetic photon in this cavity by destroying a phonon, and then this photon leaks from the leaky cavity and we end up having one less quantum of energy from the mechanical resonator. In this way, we move downstairs, and we have cooling of mechanical resonators. On the other hand, if our energy if we select the detuning, uh, if we select blue detuning, and we have two more squeezing interaction. In this case, if we start from n photon and m photon, first we can see that we create a high energetic photon, and also a one extra photon, and this high energetic photon leaks out from the cavity, but we have now one extra phonon. So in this way we move up to the stage, and we get heating of the mechanical resonator. So if we get red detuning, or if we pump the cavity on the lower sideband, we get cooling, and if we pump our cavity on the upper sideband, we get heating. So this is the message we may want to remember from here. Okay, so there is a slight digression here. Before we move to our proposal, I want to introduce some notations which we are going to see in the next slides. In order to do that, let's consider a harmonic oscillator which is interacting with two thermal baths simultaneously. So in this case, we can write the master equation for the harmonic oscillator like this, where dA are the Lindblad dissipator operator. The first two terms actually represents the dissipation from the left bath, TH, which has a temperature TH, and the second two terms corresponds to the right bath. And these G functions, basically GH and GC, includes the information from the spectral densities of the bath. And in this work, we only consider ohmic spectral densities, which is basically given here. Now coming to our problem of cooling in the optomechanical resonator. So this is the schematic diagram in which cavity is interacting with the mechanical resonator via optomechanical interaction, and the cavity mode is interacting with the hot bath, and the mechanical resonator is all coupled with the bath at temperature Tc. In order to derive the master equation, what we do, first diagonalize the optomechanical Hamiltonian using this transformation, where alpha is the ratio of optomechanical coupling to the mechanical frequency. Okay, so by following the standard Born, Markov and secular approximation, we can write the master equation of the for the system described in the previous slide like this, where the red color terms belongs to the left bath, cavity bath, and the blue color term belongs to the mechanical resonator. One extra approximation we have done here is that we only kept the term to the second order in alpha, which means that we are only interested in the weak optomechanical coupling, as alpha is the ratio of optomechanical coupling to the mechanical frequency. Okay, so by making an analogy with the laser sideband cooling, we know that in order to have sideband cooling, we need to pump the cavity on the lower sideband, which results in a beam splitter interaction. So these actually, if you see these G functions, these are at lower sideband. So if we can only have, and if you can see, we have beam splitter type interaction, but this time this is not coherent interaction, this is the dissipative interaction. So the question is, can we have this sort of dissipative interaction and still we can cool down the mechanical resonator? So this is the big question we ask. And if you see these ohmic if you see these path correlation functions, you can see this corresponds to the lower sideband. Okay, so here is the in order to explain the analogy, we show the energy levels for the optomechanical system. So if we consider the dissipative term like A or B, like the laser sideband cooling, we can create a high energetic photon. But the question is how to dump this high energetic photon in order to complete the cooling process. To answer this, our suggestion is consider another bath at temperature TR and put it with the cavity. In this case now, if we create an extra photon of high energetic photon, we can dump it now into this bath. And now this analogy is complete with the laser sideband cooling, but it in this case now we have three baths. Two are attached with the cavity mode and one is the mechanical mirror. And this is the master equation we get for this system. And remember this, we have dropped other terms which we can do actually, and we lay out the complete description in our paper, how we can drop these terms using path filtering, which I think not important in this talk. All right, so we are only interested in the dynamics of the mechanical resonators. We take the trace over the optical resonator, so this is the master equation, and we are interested in the mean number of phonon, so we write the equation for the mean number of phonon. Here is one interesting thing to note. So this is the structure of this equation is actually very similar to the number of phonon equation for the laser sideband cooling. So they share many similarities in the mathematical structure, share many similarities in both laser sideband cooling and cooling by heating schemes. So here are the results. First, we show that we plot the numerical result against analytical result. The red line represents analytics and black is for numerics. On y-axis you see the mean number of phonon, and the shaded region shows the region below the which shows the actually number of quanta less than 1, which means we are close to ground state. So here we consider the typical parameters of an optomechanical systems, and we consider three different set of parameters associated with three different temperatures for the mechanical resonators, and these are the initial number of quanta we consider in the mechanical resonator. Okay, so in this graph you can see that by increasing the temperature of one of the paths, we can actually cool our mechanical resonator near to the ground state. So this is the first important result. Now in the literature, it is well known that if more than one mechanical resonators are coupled to this same cavity mode, it is very difficult to cool down the mechanical resonators simultaneously, and it is not possible to cool down if the mechanical resonators are degenerate. The reason is that if the mechanical resonators are degenerate, then the presence of dark mode, which decouples from the cavity mode, makes it impossible to cool down the mechanical resonators simultaneously. And this is pointed out in several works. One of them is here, and please focus on this panel D. If these are the ratio of the frequencies of the mechanical resonators, and you can see if the mechanical resonators are frequencies are close to each other, it is not possible to cool it down. However, if we consider our scheme, which we sketch here, in which we have, this is the scheme in the microwave regime. We have our microwave resonator, which is interacting with the mechanical resonator. It can be one or more than one. In this case, we show that it is possible to cool down all these mechanical resonators simultaneously, and in this case we showed the two mechanical resonators. The red line shows one mechanical resonator, the other one, black line, shows the other mechanical resonator, and all these panels corresponds to different set of parameters. But the important thing is that we can actually cool both these resonators simultaneously. And to conclude my talk, we have proposed ground state cooling based on cooling by heating schemes within the experimental parameters regime, and most importantly, our scheme is valid for the cooling of multiple resonators, and our scheme shares many similarities with the sideband cooling. Actually, we established uh, a link between sideband cooling and cooling by heating scheme in this work. Thank you for listening.